Hello everyone, my name is Oscar Venegas and this is my presentation for the laboratory number 3, exploring GNN for node classification and social network analysis. Let's start. For this slide is a brief introduction of something that we already know from the classes. So basically it's an introduction for graph neural networks. So GNNs are a type of neural network specifically designed for graph structured data. In this kind of data, entities are represented as nodes and their interactions or relationships are represented as edges. Unlike standard neural networks, GNNs do not treat each data point independently. Instead, they combine the attributes of each node with information from its neighborhood, nodes, and the overall graph structure. This makes them especially useful for relational problems where the connection between entities carries important meaning. Because of this ability, GNNs have become highly relevant in many modern applications involving network or interconnected data. Dataset and application. For this project, I use the Cora citation network, which is a standard benchmark graph dataset for node classification tasks in graph neural networks. In this graph, each node represents a scientific paper and each edge represents a citation relationship between papers, meaning that connected nodes are related through references in the academic literature. The node features are derived from the content of the papers, typically represented through word-based attributes, which provide information about the topics and characteristics of each document. The objective of the task is to predict the category or class of each paper based on both its own features and its connections to neighboring papers in the graph. This makes Cora a very suitable dataset for evaluating GNN's models, since successful classification depends not only on the content of individual nodes, but also on the relational structure of the network. I use this dataset both for hyperparameter experimentation in part 2 and for the final application framing in part 3. Where it was presented as a social or relational network analysis problem. In that sense, the dataset allowed me to study both the technical performance of the model and the broader relevance of the GNNs for graph-based data. Okay, so I modified the original model so I could systematically evaluate how different hyperparameters affect performance on the Cora dataset. Instead of keeping the architecture fixed, what I made was the model more flexible and allowing changes in the number of layers, hidden dimension, activation function, dropout rate, and learning rate. This gave me the ability to study how the model depth, representation size, regularization, and optimization settings influence the learning process. Then I compared the different configurations using training loss, validation accuracy, and test accuracy as the main evaluation matrix. By doing this, I was able to identify which settings led to more stable training and better overall performance. These experiments were important not only for understanding the sensitivity of the model to hyperparameter choices, but also for selecting a stronger final configuration for the application part of the project. So what I'm going to show next is the hyperparameters that I evaluated. So basically I resume the hyperparameters in the shown table. So I modified the original model so I could evaluate how different parameters affect performance on the Cora dataset. I tested the number of layers, hidden channels or dimension, activation function, dropout rate, and learning rate. Then I compare the configuration using training loss, validation accuracy, and the test accuracy. So the model performance and graph representations. In this slide, I show two views of the project. On the left, the validation accuracy curve shows how the GCN improved during training on the Cora dataset. The model learned quickly in the early epochs, then stabilized around about 0.77 to 0.79, which suggests convergence and consistent performance. On the right, the graph visualization shows the Cora citation network, where nodes represent papers and colors represent their classes. This helps illustrate why GNNs are useful. The model is learning from both the node features and the relationship between connected nodes. Okay, I'm going to start with the results, insights from my experimentations. So as I mentioned, what I evaluated was the number of GCN layers, hidden layer size, activation function, dropout rate, and learning rate. So from the experiments, I found that moderate model complexity gave the best overall performance. Increasing the number of layers did not always help, and deeper models could reduce performance. Hidden dimension and dropout both matter, with moderate values giving a better balance between learning capacity and generalization. I also observed that the learning rate had a strong effect on how quickly and how stably the model converged. So the best results came from moderate model complexity. As I mentioned, the key observation is I used 2 to 3 layers, which is where I found the best performance. Moderate hidden size improved performance without adding unnecessary complexity. Very high dropout reduced performance, and learning rate strongly affected convergence stability. So as I mentioned, validation accuracy stabilized around 0.77 to 0.79. Okay, so this is the last slide before the references. So I would like to provide some conclusion and a few takeaways. So in conclusion, this project showed that GNNs are well suited for relational and graph-based problems. The GCN achieved solid performance on the Cora dataset, and the experiments show that hyperparameter tuning plays an important role in the effectiveness. As the next step, I would like to explore other GNN architectures, test additional datasets, and study how different graph neural networks designs affect performance across application areas. So this is basically my conclusion and potential next steps. GNNs are effective for graph structured data. The GCN performed well on the Cora citation network. Using both node features and graph connections improved classification and performance. So hyperparameter tuning was important for finding a strong configuration. Okay, the next slide is basically the reference, some of the reference that I use, or the reference that I use. So thank you very much for your attention.